Alrighty. So this first one up here is really kind of working as a big review. It's got a lot of the pieces we've talked about. So we've got our domain and range that we want to find. We've got all these other pieces. Yes. So remember, think about domain as our how far left does it go, how far right does it go. It's thinking about our x's, but it's really saying how far does this go left and right. So think about it this way. Does it ever stop going left? And does it ever stop going right? How far left and right does it go? From negative infinity to positive infinity. There is nothing stopping it. It goes all the way over. Negative infinity to positive infinity. And so we write it like this. With our range, think about how far up and how far down. So we want to know how far up it goes and what's the very, very, very lowest it can go. What is the lowest our y's go? Oh, I heard it. It was very quiet, but it was there. It's never going below this spot, right? So it comes down and then it goes wiggle squiggle and then it goes right back up. So it's not going below here. So the very, very smallest my y's can be is this -4. So we write that as a -4. And the biggest it can be, very clearly we're going up here. So that's going to be when we have our positive infinity. So if it helps you to think about it like this, draw out these arrows. Think how far left and right for domain, how far up and down for range. Is this a function? Yeah. Functions, and we're doing our vertical line test. So we grab our yardstick and hide it. That's when we're doing our vertical line test. It's never crossing more than one point at a time. So yes, this one is a function. Is it a one-to-one function? That's when we're doing our vertical line test, is how we know. If we did our vertical line test for function, how do we check for one-to-one? Sideways. Does it cross the graph at more than one point when I hold it this way? So does it pass the horizontal line test or fail the horizontal line test? It fails. It fails several times. In fact, it fails everywhere. There is not one place where it does not cross more than one time. So this is not one-to-one. No. It fails the horizontal line test. You don't necessarily have to put that part, but I'm just letting us know why. So is this discrete, continuous, or neither? What do you think? It is continuous. There's no holes, there's no problem spots, there's no weirdness going on. It is just one end to the other, wiggle squiggle. So this is continuous. Okay. Questions on that one, on part one? Cool. All right, so then we have two questions down here in question number 2, where we ask you if these are linear or nonlinear. So I'm going to label them just because they weren't. So I'm going to call this one A and this one B, just because otherwise things are annoying to talk about if we don't have a way to label them. So for A down here, and I know it's very small and very low. I'm going to change the view real quick. What do we think? Is this linear or not linear? nonlinear. How do we know it's not linear? It's a power of 2. So this is nonlinear. If we have a power of anything other than 1, it is not linear. If we have any weirdo crazy things happening to our x, like square roots of x, it is not linear. What about b? What do we think about this one? This one is linear. I heard it. Fancy L. This is linear. I could write this as a y equals mx plus b. To do that, I would need to add my y to both sides and subtract 15 from both sides. We could do it. This is in our general form or our standard form. So if you think about it that way, this is the same thing as if we had an ax plus by equals c kind of situation. It's structured just like this. It's our standard form or general form. We don't have to switch things around into a slope-intercept form, but we could if we needed to or if we wanted to. When we get into graphing lines, we probably will. But for now, all we need to do is be able to recognize that it is a line. If I graph that, it would be a line. Questions on these? Cool. We are going to be in your notes packet again. Shock of all shocks. Oh my gosh. We are going to be on page 7. We're going to do 7 and we'll get to the top of 8. But that means we are starting with some definitions. So we're going to be talking about symmetry today, and we're going to have a couple of tools we use when talking about it because it's one of those things that is sometimes hard to picture in our heads, but we're going to do our best, okay? So we're going to work through some stuff. So there's 2 kinds of symmetry that we're going to look at. We're going to have line symmetry and we're going to have point symmetry. I'll explain those. And then there's 2 very, very special kinds of functions based off of both of those. And we're going to talk about these the whole day. So the first thing I want to bring up is we're going to talk about line symmetry. And what line symmetry is a graph that's reflected across a line. I promise I will show you what I mean by that. Sometimes when we write definitions, it feels like we write in a different language. I promise I will always get things explained a little bit more. A graph. I'm going to write a little bit bigger. That's meant to be in it. Can be reflected across a vertical line and still match up. What that means, like, because that's like super duper mathy way of saying it. If I have a graph and I can take my graph and flip it over and it still matches up. So I could fold it or I could flip it. Either way, it's doing the same thing. If I can fold it in half or if I can flip it over and they line up, that is line symmetry. Because it's flipping over a line here. The single lady. So it's line symmetry because it's flipping over a line. It's a rotational like this. Then our other one is point symmetry. Point symmetry is a graph that can rotate. It's not a reflect this time, it's a rotation. Around a point. and match up. So again, I'm going to show you a little sketch of what I mean by that. If I can take this picture, and I know it's squiggly, but I'm using a straight line, and I can rotate it a half circle, so I'm just taking it, doing one rotation, and it lines back up, that's when we have point symmetry. So it rotates upside down and then lines up. So you will never have something that has both line symmetry and point symmetry, except for a horizontal line. It's literally the only thing, but we're not doing that. So even functions and odd functions are very specific cases of point symmetry and line symmetry. So an even function has line symmetry but it's specifically over the y-axis. There's a way to check it mathematically that we are going to have to talk about very, very briefly and do a little bit of, but it's not going to be something we do tons of. And that's, I'm going to get it down. If you substitute in minus x for x. So like if we get an equation y equals x squared, and I put minus x in its place, and we simplify it as much as we can. With an even function, we're going to get back exactly what we started with. The equation doesn't change. And I know it's long. Sorry. The equation is the same. That's what I'm putting EQ as. And just like even functions are line symmetry, odd functions are a point symmetry specific thing. So an odd function is, or an odd function, there we go, has point symmetry through the origin, so through 0, 0. It has to go through 0, 0 to be an odd function. And again, we can test that with the equation, substituting in that same minus x. But this time we would get our equation that is essentially the opposite of y. So if we substitute in minus x in place of x, and then we do all of our distribution and stuff, we should get the opposite, a negative number. And I will walk you through that, I promise, because I know especially for the even and odd, we just wrote a sentence that felt like Greek. I get that. It felt like another language sometimes when we write definitions down. But we're going to look at these pictures down here, and we're just below where you've written your definitions, and we're going to decide if they have point symmetry or line symmetry. And I'm going to pass out a piece of paper for you guys. It's called patty paper. It's basically tracing paper, and we're going to use this to help us figure out our symmetry. I have literal boxes of this. I can always grab more of these, so if ever you need some of these for working on homework or when we're looking at quizzes and that kind of stuff, I'm just going to put 2 out for each of you guys. And you can use both. You don't have to use both. I'm just going to put a few of them out. But these are, I think, the easiest way for us to see the symmetry and when things line up and when they don't. So we're going to use these. You are going to want to use a non-gel pen with this paper. It really does not like gel pens. It works pretty good with pencil. Works well with ballpoint pen. It just doesn't work with gel pen. It beads up. Nice. And it's really bad at markers. Do you know these markers on these? It will just basically make dents. It's really bad at markers. So it's just like too threatening. Whatever. So here's some of these. We're just going to use it like a tracing paper. And if you need more, again, I have tons and tons of ducks. So, I've been using this box for like 2 years and I still have a giant stack in here. So, like, I can always get you more. Totally cool. So, we're going to start by looking at these pages here. I had a giant version of it and now it's disappeared. That's okay. I'll use this. There we go. All right, so when we're looking to try and figure out the type of symmetry we have here, especially when we have graphs, that's when we're going to grab our, this is my version of the patty paper right now, especially when we have a picture. What we're going to do is we're going to grab our paper, we're going to look at our graph, turn off the touch screen so it doesn't keep yelling at me. There it is. I'm going to save it. And what I want you to do is I want you to trace our line, but I want you to also kind of include our axes, just so we can look at stuff. It's not super important that we include our axes, but like we're just making like a little baby sketch. It's like a baby sketch, but with helpers. So we're tracing it. Because if we have line symmetry, I could take my picture here and I could flip it this way, I could flip it over, and it would line back up. So if I can flip it or fold it in half and it lines up, that's line symmetry. So does this have line symmetry? Do these line back up? That's this blue line and that blue line do not line up. So this does not have line symmetry. That's what we can tell from that. If I flip it and they don't line up, no line symmetry. Does this line back up if I rotate it? Do those line back up? Yeah. So this has line symmetry. If I this has point symmetry, because what's happening is I'm rotating it around a point like this. So if I can rotate it around a point, basically turning it into a spinner, then that is when it has point symmetry. So this guy here has point symmetry. And if you just put the word point, I'm totally okay with that. It is point symmetry. It's the only time we're going to use that. The reason it's sometimes helpful to mark the axes and things is because if when we rotate and get our point symmetry lined up, our axes are still lined up, that's when we have our super duper extra special case where it is our, don't want to say backwards, our odd function. So if when we do the rotate, our little origin still matches up, that's when we have our odd function. Those are super duper rare and super special. So then let's do the same thing with the next one, the one on the right. We want to see if this is point symmetry, line symmetry, or what have you. Here's what I intended to use for my patty paper. So again, I'm going to come through and I'm going to look at my picture and I'm going to trace it. And I like to just put my little axes on here, or you can just mark the origin, or you can just keep eyes on stuff. But so I'm just making my little sketch here. So let's see if this has that point symmetry like that one had. If we rotate it, does it line back up? You didn't move it anywhere? No, so I went from an upside down view to a right side up view. Those are not going to line up even if I make them play nice. But if we flip it, if we reflect it, do those line back up? If I flip this over, does the blue line and my little black line over here line back up? Yeah. What this is telling us is if I fold this in half, these match up. So this point right here, this line that goes right through the middle, that is called our line of symmetry. Not something you need to know right now, but it'll come back up later as we go. And it's all about how it's matching across that line. So that one has line symmetry. You can think about it folding right through here. These pieces line up. These pieces line up very, very matchy-matchy. On our point symmetry, it's that these guys rotate around and would line back up if I was to spin it. So point symmetry makes a spinner. Line symmetries fold on each other. It's another way to think about it. Okay. We're going to do 2 more like this. So let's see if we can figure out point symmetry or line symmetry on these 2. I'm going to grab this thing again because it's just easier to manage. So remember that that has those arrows on either end. So just because it has an arrow doesn't mean it has to match up exactly with these lengths. Look at where the squiggles happen. So I'm going to kind of set up down here. I'm not going to focus up here. Look at where any wiggle squiggle stuff happens. So I'm going to mark these axes just because it helps me see when things are moving. And then this is where our curve is. And it does have arrows on both sides, so it helps you put those in. Because what I want to know is, does this have line symmetry? What do you think? If I flip it, does it line up at all? Does this have point symmetry? Yeah. It doesn't matter that it's way down here. That's okay. If I can spin it and it lines back up, doesn't matter that this side's super long and this side's super short, it's still lining back up. So if we can spin it and it lines back up, that's when we know we have point symmetry, because it's spinning around this point. That's what's happening. It's a point that's giving us that data. So this one has point symmetry. I don't know where my stylus went. I'm losing pieces. There it is. So this one has point symmetry. And again, you can just put the word point. All right, one more like this. And we've got this kind of W-shaped one. Wonky W. And again, I can always get you more papers, so if you use as many as you want, but you don't need tons of space on it. So if I take this graph, and again, I'm going to copy down kind of all the bits. So it's like my little travel version of the graph. I'm going to take it with me and go. Does this flip and line back up? No, I can't I can't make this line back up anywhere. So we know it does not have line symmetry. Does that automatically mean it has point symmetry and we don't even got to test it? Because does this have point symmetry? No. I mean, it kind of looks like it would make a half decent puzzle piece, but that's not symmetry. So it's entirely possible for it to not have any symmetry at all. It does not have to be symmetrical. So if it does not have line symmetry, and if it does not have point symmetry, it just has none. None is an option. And in fact, none would be a very common thing we see symmetry-wise. So this has no symmetry. It doesn't spin and it doesn't reflect. Okay, so when we're looking at graphs, we're really just going to be looking at, does it rotate or does it flip? Flip as a line, rotate as a point, because when you rotate it, it spins like a fan or like a spinner. So what we're going to do on the next page, we've got 3 more graphs to look at, and we can kind of see what we think about them. But what we're going to do is we're going to be actually looking at these algebraically and how we do that, which is a kind of obnoxious way to do it, but like, it's a thing. And move. There we go. So what we're going to be doing is we're going to try and figure out if this is even or odd or neither. Even is a very special case of our line symmetry, just making sure I don't mix things up. So even is when we have line symmetry directly over the axis. So it would have to, it's not the right shape, I know that. So if we had our flip that worked directly over our y, that's what I mean by over the axis. So we would have to flip right there for it to be even. Odd is when it has line symmetry through the origin. So it would have to spin right through the 0 point. So odd is point on 0, 0. So it has to be point symmetry on 0, 0 or line symmetry on the y-axis for that to happen. We can't always tell when looking at the picture. Sometimes they're super close and look like they're super close even when they're not. So the way we're going to do this when we have an equation is that minus x thing that I mentioned at the very, very beginning. So we're going to look at this one with the equation, and then we'll look at the picture and see what's going on here. So what this one is, we're going to take our x cubed minus 4x and try and do this algebraically. Means I'm going to take this equation right here. Remember, this guy just means y. And I'm going to say, what if my x was actually minus x, or minus 1 times x? So our equation here says we need to take x and cube it, and then we're going to minus 4 times minus x. So we're going to substitute those pieces in, and then we need to do a little bit of actual thinking. Oh. What does it mean for something to cube? What does that mean? We've dealt with square quite a bit, but not as much on cube. What this means is to multiply by itself 3 times. So if we were to write that out, you don't have to do this, but I'm going to do this part. If I write this out as minus x times minus x times minus x. So that's what this guy turns into. Are we going to wind up with something that is positive, or are we going to wind up with something that's negative? A negative times a negative times a negative. What do you think? Because a negative times a negative becomes a positive, right? So if we just looked at two of them, these two guys, minus x times minus x, we're going to get just a positive x squared. Because a minus times a minus cancels out, right? But then we have this other minus x here. So this is the exact same thing as if we had a negative x cubed, right? See that? That's probably the weirdest part of this. These things all mean the same thing as this minus x cubed up there. What happens when I have minus 4 times minus x? We have a minus 4 and a minus x. What's that going to be? It's going to be a positive. So this is the same thing here. That was the weirdest squiggle I've ever drawn. There we go. This is the same thing as plus 4x. So when we substitute in that minus x in, we get this. What we want to know, and the way we can test if this is odd or not, is if this is the exact same thing as if I multiplied through by minus 1. So if I take y times minus 1, meaning I'm going to take this whole piece. I'm going to color out the border here so I can use this space. There we go. So if we take this whole equation of y, our x cubed minus 4x, and we multiply it by negative 1. So times negative 1. And I know they're right next to each other here. There we go. So if I distribute that through, we're going to have minus 1 times x cubed, also known as minus x cubed, and minus 1 times 4x, we get plus 4x. So the way we're checking this, just so I can put it up here, we're going to substitute in our minus x. And then for our odd, we take our y times minus 1. So our equation, or our f of x, whatever we call it. Do these match? Equations. Yes. We got the same thing when we multiplied y by minus 1 that we did when we put minus x in. If those two things equal each other, what we have is our odd function. So this is odd. What that tells us, and I'm going to show us using the picture things that we've been using in our little sketch. What this shows us is that on this picture over here, when I trace this out, even though I know it's a little small, we know it doesn't flip, definitely. So we know it's not got line symmetry, for sure. And when it rotates, our axes are lining back up. So our curves line up and the axis is lined back up, because it's spun right on the 0 point. So that's what the very, very special odd function is that it spins right on the middle. This point is going to line up exactly with this point. This point is going to line up with this point. They're very, very symmetrical. It would make a very decent fan, like spinner kind of fan. So these are the most kind of obnoxious ways to do these. This is not going to be something we have to do tons and tons, but it is something we are supposed to know how to do. Okay, we're going to do another one because these are weird, and I get that. So let's look at the next one. We're going to see if this is even, odd, or neither. The process is the same. We're still going to substitute in that minus x into our x's. We want to see what's going to happen. So to test, we're going to take our 2 times our minus x. That's the piece we're substituting in to the fourth. Minus 6 times our minus x squared. Now when I take a negative number and square it, are we going to get a positive number or a negative number? Positive. And negative times a negative is always positive. So if I take minus x times minus x, we're really just getting a positive x squared. So this is the same thing as having our 6x squared. What about when I have to the fourth? Is that going to be positive or negative? And we can always think about that the same way we did on the last one. I'll write it out. I'm just moving that piece down. So if we have our minus x to the fourth, that's the same thing as minus x times minus x times minus x times minus x. 4 of them. That's what it means to be to the fourth. Well, we just said that if I did 2 of them, that's going to be positive. And then I have another 2 of them, so that's going to be positive. So if I have a positive and a positive, what are we going to have? It's a positive times a positive. We know this is going to be a positive x squared. And we know this is going to be a positive x squared. What's positive x squared times positive x squared? Algebra 1, exponent review. Oh, snap. That 2's still coming down. That's this 2 from in front up here. X squared times x squared, we're going to get x to the fourth. So when we substitute in that minus x, what we're doing, and if you look in your books, it's going to say f of minus x. Oh, snap, what? We substituted in that minus x. Is this the exact same as what we started with? Yeah. If it is the exact same, no change, no deviation, that means it is our very, very, very special even, where we have our line symmetry that's going to be over the x-axis, and I'm going to show you what that looks like. So if we have, I'm going to do it that way. Axes. This one. Well, we can definitely see it is not point symmetry. There's not a way I can flip it and have that go. But if we reflect it, we can see how those line up exactly, and that my x-axis is still lined up and my y-axis is still lined up. Since it's reflecting this way over that y-axis, that's why we're getting our even function here. Because everybody lines up nice and tidy. These guys match, these guys match, these guys match, these guys match. It's very, very symmetrical over this line. So it's all about how they're lining up. That is going to be where we stop for today, for sure. There is only one question on homework 2 that actually talks about symmetry, and I believe it's number 22 on the homework. So there's only one question for that to do. I'm sorry, 22 and 33 both mention symmetry. Only one of them actually gives you an equation. So give it a shot, see what we can come up with. It is very similar equation-wise to this one. So think about that. Okay, I'm going to put this up here. We are going to do a very, very, very short skills check tomorrow just to kind of give us an idea of where we are, because we have a quiz in a week, and so kind of over the things we've done. We're going to do a quick skills check. It will go in as homework. It's not going in as a quiz. It's not a quiz. It is a skills check. On homework, I tend to not grade every single question. I'll get them passed back to you tomorrow. But the skills checks, I will grade every single question and give you feedback on it. But I just don't have time on all the homeworks to grade every single question for every single person.